Hi, we are from Runtime Error, and we'll be presenting about mixed assembly language for our group project. So this is our team members. First is Tashana Anak Perempuan Santiran. Secondly, Ilin Rujasmi binti Abdullah, which is me. Third, Alia Nadira binti Muhammad Sazli. And lastly, Heng Wei Kiok. For part A, it will be presented by Alia Nadira first.
For part A, individual teacher. So, Heng Wei Kiok choose shortcode in descending order, and she will explain what happened in shortcode in descending order. Ili choose shortcode in descending order, and me, Alia, choose find the second largest code. Display correct even or odd in this position will explain by Tashana. Okay, I will pass to Wei Kiok about branching and looping.
In part B, we will explain how branching and looping are used in our individual feature. Hello, my name is Heng. In this program, we use loops and branching to sort an array in ascending order using the bubble sort method. Let me explain how it works. For the outer loop, this loop goes through the entire array starting from index 0. Then, register T0 keeps track of the number of iterations. The loop stops when register T0 equals the array size register T1, which means the sorting is done. For the inner loop, it compares adjacent elements, array J and array J plus 1. The inner loop counter register T2 controls the index of the current element. The loop stops when register T2 equals the register T1. We use a branching condition BLE, which stands for branch if less than or equal to check if two adjacent elements are in the correct order. If they are, we skip the swap. If not, we swap them. Register T5 contains array J, while register T6 contains array J plus 1. For example, if array J is bigger than array J plus 1, the program swaps the two elements.
My name is Ilin Rujasmin, and I will be presenting about descending order. For outer looping, the loop outer loop descent iterates through the array starting from index 9. Then, register T0 acts as the loop counter. The loop stops when branch or not equal register T0, register T6, outer loop descent. For inner looping, the loop inner loop descent iterates through the array from index 0 to the current outer loop index. Register T2 acts as the inner loop counter. And the loop stops when branch on equal register T2, register T0, next pass. It decides if a single pass through the array is complete. Next is branching. Compare adjacent array elements A equals to array J and B equals to array J plus 1. Decide whether to swap the elements based on whether A less than B. If A is less than B, then you will swap them.
Thank you, Ili, for your descending order explanation. So let's continue to my part. First of all, my name is Alia Nadira. In this section, I will explain how looping and branching are used to find the second largest code value in the array. I will explain the looping part. This part, the looping part. The loop used here is second loop. Is called second loop. This loop is responsible for calling to the array one value at a time, starting from index 2 because the first two elements are used to set the largest and the second largest. The register T3 acts as the loop counter. During each loop cycle, the instruction LW, which means load word T4 and 0, and in the current T0, loads the current array value into T4. And then the loops will continue running until the condition B equal, which means branching, equal to T3, 10 short second is met. This means when the counter is 10, when the counter, which is I, which is T3, is 10, the loop stops and the program jumps to display the second largest value. Will go to the short second, which means the second largest value. So overall, looping allows the program to check each element in the array one by one in the organized way. Next, I will explain how the branching is used. Branching is used to compare the current array value with the store largest and second largest values. We will go with the first instruction for branching. The instruction VGT, which means branching greater than. So in this value, we will compare the T4 with T1, which if T4 is greater than T1, we will jump to update both. If the condition met, we will jump. The program branches to update both whether the largest and the second largest values are updated. If the value is not larger than the largest, which means T4 not larger than T1, the instruction will go to next instruction which is BLT branching less than. Is T4 less than T1, it will go to check second to check whether it is less than the largest, so it can be compared with the second largest. So first it will see if the T4 is larger than T1. If not, then it will see if T4 is less than T1. But if none of them, the condition is met, the program will jump to next second and continues to the next loop cycle that we will use looping. So branches allow the program to make decision and update the register only when necessary, when it need, instead of assigning values without checking. That's all for me.
Finally, we have the call, looping, and branching logic. The display loop uses a back, which is branch if equal instruction, to stop once our counter reaches 10. To check if an index is even or odd, we use ANDI, T2, T1, 1. This performs a bitwise AND on the index. So if the result is 1, the index is odd. If the current index doesn't match what the user asked for, the BNE instruction skips the printing phase and jumps straight to the next iteration. So this ensures we only display the specific values the user requested.
Let's move on to the next part, where we will explain how the input is processed and stored based on our individual feature. How input is processed and stored for ascending order sort. First, address of array loaded into register S0. Next, initialize the size of the array, 10 elements. Initialize the outer and inner loop counter to 0. To compare elements in the array, we use register T2 to calculate their memory address. Then, access the elements using shift left operation, which multiplies index by 4. Store word instruction used to compare and swap elements. Last, sorted values are stored back into the array.
Next is how input is processed and stored. Array valcos is preloaded into memory. No drag using required. After loop begins with I equals to 9. It will store in register T0. Array J store in register T3, and array J plus 1 will store in register T4. Set less than, compare two values, then, and it will swap. Vault codes and array updated and printed in descending order.
So for this part, I will explain how input is processed and stored for second largest code. Unfortunately, in this section, in my part, second largest code, there is no user inputs required. The program will use predefined data stored in the array vault codes in memory. The base address of the array is loaded using load LE T0 vault codes, which means load address from the data segment. Then array values are loaded in register using the LW, which means load words T1, 0. The first value is stored in T1 as the temporary largest value, and the second value is stored in the T2 as the temporary second largest value. And then after the instruction, we go to BGT instruction, BGT T2 T1 swap, bunch greater than, to check if second is greater than, is the second largest value is largest than the first largest value. The condition it will jump to swap. This instruction to ensure the correct order between the largest and second largest value. So even without user input, the program still process the data by reading from memory, storing value in register, and preparing them for future comparison. So that's all from. I will continue now. My teammate will continue to the next part.
Now let's look at the actual code for initializations and input. The program uses LA to load the address of the array into S0. To get the user's choice, we use syscall4 to print the prompt, followed by syscall5 to read the integer data type. This choice is moved into T0, and our index counter T1 is reset to 0 to prepare for the loop.
Now, let's move on to part D, where we will explore what happens inside the registers, text segment, and data segment in our individual feature. In this program, we use several registers to manage the sorting process. Here's a quick overview. Register S0 stores the base address of the array vault codes. Register T0 is the outer loop counter. Register T1 holds the array size. Register T2 is the inner loop counter. Register T3 calculates the offset for accessing array elements. Register T4 stores the current array element's address. Register T5 holds the value of array J. Register T6 holds the value of array J plus 1. Register A0 is used to print the array elements and display messages. In the text segment, the program defines the steps for sorting the array in ascending order. First, initialize the outer loop counter to 0. Then, the outer loop iterates from 0 to 9, comparing adjacent elements in the array. The inner loop compares array J with array J plus 1. If array J is greater than array J plus 1, swap them. Store array J plus 1 array J using store word. The process is repeated until all elements are sorted in ascending order. In the data segment, we define the data elements used in the program. Vault codes. This is the integer array that holds the input values to be sorted. Sort ascending MSG. A message that is displayed before showing the sorted array. Space. Defines the space between numbers when they are displayed. To move to the next array element, we calculate the offset using the SLL shift-left logical operation. This ensures that we access each element correctly during the sorting process.
Next, we move on to what happened inside the registers, segment and data segment. For descending order, register S0, the purpose is base address of the array of codes. Register T0, outer loop counter. Register T1, pointer of current array element. Register T2, inner loop counter. Register T3, hold value array J. Register T4, hold value array J plus 1. Register T5, hold result of comparison. And lastly, register A0, hold value or message. Next is what happened in text segment. Firstly, the loop starts when I equals to 9. Then the outer loop controls the total number of passes needed to sort the array. It will compare elements array J and array J plus 1. If it finds out array J is less than array J plus 1, it will swap the element. And then it will continue with the next pass. The outer loop counters registers T0 is decremented, and the process continues until all of the elements are sorted. Next is after the sorting is complete, print sort descending message and element by element with a space between each number. Lastly, the program returns to the menu. We move on to what happens in data segment. For bulk codes, integer array that contains the input values to be sorted. For sort, there's sort descending message display before the sorted array. For space, it is for space between numbers. Moving pointer to the next integer is immediate. Register T1 equals to register T1 plus 4. The comment is move to next memory address.
Okay, thank you, William, for the explanation. So I will continue my explanation with second largest code. So what happened inside register, text segment and data segment in second largest code? So let's start first. So T0, T1, T2, T3, T4, which means temporary 0, temporary 1, temporary 2, temporary 3, temporary 4. So what the purpose of it? So we will start with T0. So T0 will hold value pointer to current array element. The purpose of the T0 is pointed to current array element. So T1 it will hold value largest value, and T2 it will hold value second largest value, and T3 it will hold value for loop counter, which means index as we know as I, and T4 will hold the current array value. So T means temporary means it's not stay, it's not kekal. Will hold the value just for a while before it will change the other value. So for A0 means argument. The purpose of A0 means value message to print. For example, if T4 move to A0, which means T2 will usually move T2 to A0. The value in T2 will move to A0, and then it will print the value in A0, which means T2. That's why value message to print. If you want to print in T2, but if you want to print the value in T1, then we move the value T1 to A0 because we want to print that value A0 argument. Okay, value message to print. Next, register V0, which means V value or the value. V0 usually we call system call the selector. V0, yes. So we use V0 using this system. We call the system. Which part we want to call. So and then for basic console instruction flow and branching. That's all what happened in register. Okay, so let's explain what happens in the text segment of the program. First, the program loads the first two elements from the array. These values are stored in the register and are used as the initial largest and second largest values. Next, the program compares the two values and swaps them if needed. This step ensures that T1 stores the largest value and T2 stores the second largest value. After that, the loop is initialized starting from index 2 because the first two elements have been processed. The program then loops to the remaining elements in the array. For each value, it is first compared with the largest value. If the current value is larger, the program updates both the largest and the second largest values. Otherwise, the program checks the value against the second largest. The loop stops when the index is 10, which means all elements have been checked. Finally, the program displays the second largest value and then returns to the menu. Okay, let's moving into the technical implementation. Let's look at the data segment for our second largest code program. We have two primary components defined here. First, bulk codes, which is our integer array containing the values we need to process. Second is second highest message, which is the output string used to display the final result to the user. To navigate through the array, we use a pointer-based approach. Since we are dealing with standard integers, each element occupies 4 bytes of memory. As shown in the code snippet next second, we use the add instruction, ADDI, add immediate, this action to increment our pointer register T0 by a value of 4. This effectively shifts the pointer to the next integer in the sequence, allowing us to iterate to the list efficiently. Now that the data structure is set, that's all for me. Let's go to another slide.
Beyond our temporary save registers, we use A0, which is the standard register, for passing values to be printed. B0, the system call selector, which tells the machine whether we want to read an integer, print a string, or exit. And finally, the program counter, PC, which automatically moves through our instructions and handle jumps to different labels. To keep track of all of this data, we use specific registers. So S0 holds the base address of our word code array. S1 stores the array size, which is 10. T0 captures the user's choice, 0 for even, 1 for odd. T1 acts as our loop counter or current index. T2 stores the result of our parity check. And finally, T3, which is used to hold the specific memory address we calculate during each iteration. Moving into the text segment, which contains our actual logic, where we follow 6-step flow. First, to load the array base and size. Second, it prompts the user to choose between even or odd indices. Third, to initialize a counter to start at the beginning of the array. Fourth, it enters a loop where it checks the condition and determines the parity, whether the current index is even or odd. And then for the fifth, we use the parity matches to use the user's choice. It can load and prints that value. And finally, it repeats until it reaches the index 10, at which one point it returns to the main menu. Let's begin with the data segment. This is where we define the variables and constants our program will use. First, we have word codes, which is our primary integer array. And we also define several elements, even odd prom, to ask for user input, space for formatting, and new line for readability. Finally, there's an exit message to let the user know when the program finishes. So on the right, you can see how we calculate a memory address to access an array value. So we use shift left logical by 2 to multiply the index by 4. Since each integer is 4 bytes, then add to the base address, which is register S0.
Now, I'll be demonstrating the features of the Vault Security System program. Upon launching the program, the first thing you see is a prompt asking you to enter 10 access codes. These codes must be between 1 and 9,999. If an invalid code is entered, the program will ask the user to try again. Here, I will enter some access codes for demonstration. Once all 10 codes are entered, the main menu will appear. Let's start by choosing option 1 to display the highest access code. As you can see, the program identifies the highest access code and displays it for us. Next, let's choose option 2 to count the number of even and odd access codes. The program will display the count of even and odd codes. Let's now move to option 3, which allows us to search for a specific access code. You can enter any code, and the program will check if it exists in the list. Now, let me enter a code that doesn't exist in the vault. As expected, the program tells us that the access code was not found. Then, I will enter an access code that exists in the system. As you can see, the program successfully found the access code in the system. Once we're done exploring all the options, we can exit the program. Let's select option 4 to exit. Now, let's explore options 5, which allow us to sort the codes in ascending order. As you can see, the codes are now sorted in ascending order. Next, let's try option 6 to sort the codes in descending order. As you can see, the codes are now sorted in descending order. Option 7 allows us to find the second largest access code in the vault. Let's select this option. As you can see, the program has identified the second largest access code in the vault and displayed it on the screen. Finally, option 8 lets us display codes located at either even or odd index positions in the array. Let's give this a try. Let's first try entering 0 to see the codes at even index positions. The program displays the access codes located at even index positions in the array. Next, let's try entering 1 to view the codes at odd index positions. As expected, the program now displays the access codes located at odd index positions.